Hello. Today our team with number 21101 will be presenting the Automatic Floodgate System, or AFGS, sponsored by Bottled Water District. The success of our project was thanks to our mentor, Dr. Samuel Peffers. Our team members included in this project are Esteban Hernandez, Gildardo Hernandez, Timothy Cover, Selena Meguer, and Alfredo Espuro. First, we will talk about the overview of Bottled Water District. Water has been using mining operations of gates since 1941, and to this day continues to operate these 500+ gates manually. Such gates incorporated in Berge Water District cover over 13 acres of land and water millions of dollars in product generation. With the large number of gates and water dependability, employees have high workloads and stress. More specifically, their workload is caused by the manual operations of more than 250 gates each and the on-call duty of gate adjustment 24/7 for 7 days straight. Next, I will play a video how the employees, known as ditch riders, operate the gate manually.
The objective of this project is to design an autonomously controlled floodgate system for a barred water district. With this system, the operator should have the ability to monitor and adjust the floodgates accordingly. These adjustments shall be able to be made from a centralized office, which is at barred water district, or from a mobile device that will be supplied to the ditch rider. This shall be less strain on the ditch riders and their cars since they won't have to be driving up and down the canals.
Here in the hardware section, we begin to take a closer look at some of our major key components to our system, starting off with our electric motor, which is a Dayton 1/4 horsepower DC motor, and it has the capability to produce sufficient torque to adjust the gate up and down as needed. Moving on to our gate microprocessor, we use the Industrial Control Links Modulus Combo IO remote terminal unit. This has the ability to control the electric motor, receive data from the water level and gate position sensor, receive cubic feet per second commands from the master processor, and send current cubic feet per second to the master processor. Now, for our microprocessor, we use the Industrial Control Links Modulus Com Module remote terminal unit. This processor has the ability to connect to the internet and send cubic feet per second commands to the gate processor and upload cubic feet per second data to the internet website. Next, we begin figuring out our power subsystem, which uses two high-quality solar technology 190-watt 12-volt monocrystalline solar panels to be charging our VMAX tanks AGM 12-volt 125 amp-hour sealed lead-acid batteries. And included in our power subsystem, we connect both the solar panels and batteries to a Binnen 30-amp PWM charge controller. This will prevent any overcharging and allows for better monitoring of the battery health and provides the solar panel power output. These three crucial components power our entire gate system 24 hours a day, 365 days a year. Furthermore, for the receiver and transmitter, we chose the ICL VHF 5-watt radio modem coupled with an omni-base antenna used at the master site and a Yagi antenna used at the gate site. These antennas and radio modems send and receive cubic feet per second data from both the master site and gate site. Looking at the water level sensors, we decided to use an encoder, which measures the water level at the gate. Lastly, for the gate position sensor, we use the same encoder from the water level sensor, but now it is calibrated to measure gate position.
Now I'll explain the functional flowback diagram of the automatic floodgate system. How the system works is that the operator first inputs a desired cubic feet per second or CFS command to an internet-capable device, which is connected to the website to control and monitor the gates. Once the command is inputted, the website sends the CFS to a master processor, which is physically wired to the internet via an Ethernet cable. Then the master processor sends the CFS to a radio modem. Keep in mind that both the master processor and the radio modem are powered through an AC outlet using an AC to DC power transformer. Continuing, now the VHF radio modem sends the CFS to an omni-base antenna that transmits to a JAG antenna, which delivers it to a connected VHF gate radio modem. Once at the radio modem, the CFS is transferred to the gate processor. Once at the processor now receives data from both the gate position and water level sensor to calculate the current CFS. Once calculated, the processor sends the command to an electric motor to adjust the gate to the desired CFS based on the current water level and gate position. The electric motor now moves the gate through a speed reducer to increase torque. Keep in mind that the solar panel energy goes through a charge controller and to a battery to charge it. Now the battery powers both the water level and gate position sensor, the electric motor, the gate processor, and the VHF gate radar modem. Now that the gate has been adjusted, the gate processor once again receives data from the water level and gate position sensor to calculate the current CFS flowing through the gate. Once it has calculated the CFS, it sends it back to the website the same way it came every 2 seconds. Next, I will play a video of the different hardware components of our system.
Here is an aerial view of the omnibase antenna on top of Barge Water District's office. Displayed here is the antenna cable from the master processor to the omnibase antenna. Shown here is a master processor and the AC-DC transformer to send and receive CFS data. To the left in yellow is the YEG antenna. The largest solar panel shown on the lower right hand corner is the one currently used in our system, which is utilized by the charge controller, batteries, and fuses to power the different processors and the fuses at the gate shown here. Displayed here is the CFS gauge that ditch riders use. On the upper middle section, we see the gate position sensor. To the left, we see the water level sensor, and inside the enclosure to the right, we see the gate processor and its respective fuse box. And this is the finished automated floodgate system with the group who made it possible. I would like to conclude by stating that the automated floodgate system meets the requirements set at the beginning of the project by the project sponsors and its stakeholders.
To finish up this presentation, our team would like to give a special thanks to our references starting with Nicholas Barr, manager at Barge Water District, for trusting in us in the creation of their automatic floodgates and providing the necessary information for the understanding of the Barge Water District. To our instructor, Dr. Samuel Peffers, for providing us with the guidance, motivation, and feedback throughout the project development. He made sure that our team delivered a great project to the stakeholder, which thanks to that, we completed our project successfully. To Sarah Mayer, sales consultant at Industrial Control Links, who aided the team to select the correct hardware for the completion of the system. And last but not least, we want to thank Brian Henry, engineer at Palo Verde Irrigation District, for guiding us in the correct direction and for providing knowledge on his current automatic floodgate in Palo Verde. Thank you. We hope you enjoy our presentation.